Right now, somewhere not far from where you're lying, there's a wire running through the wall. And inside that wire, electrons are doing something strange. They're not flowing in one direction like water through a pipe. They're actually vibrating back and forth, 60 times every second, in a kind of tiny, synchronized dance. And that dance is connected to other dances happening in wires throughout your house, your neighborhood, your city, and across hundreds or even thousands of miles of cable and towers and transformers, all the way back to some massive spinning machine in a power plant that might be burning coal or splitting atoms or catching the wind. The whole thing, every light, every outlet, every hum you've ever heard from a refrigerator at 3 a.m. It's all part of one enormous, interconnected machine. And I mean that literally. The power grid is often called the largest machine ever built by human beings. And that's not an exaggeration. It's a single, continuously operating system where everything has to stay in balance every second of every day, or the whole thing can come apart in ways that are genuinely terrifying. But here's the thing. Nobody planned it that way. Nobody sat down with a blank sheet of paper and designed the grid. It grew. It evolved. It was argued into existence by stubborn, brilliant, sometimes ruthless people who disagreed about almost everything. What kind of electricity to use, how far it could travel, whether it should be controlled by private companies or the public, whether it was even safe to put in people's homes. The grid you rely on tonight is the result of over 140 years of invention, compromise, catastrophe, and improvisation. And honestly, the fact that it works at all is one of the most impressive things our species has ever pulled off. So let's start at the very beginning, and I mean the real beginning, before there was any grid at all, when electricity was basically a party trick. For most of human history, electricity was a curiosity. People knew about static electricity. The ancient Greeks noticed that rubbing amber with fur could make it attract small objects. And the word electricity actually comes from the Greek word for amber, electron. But for centuries, that's about as far as it went. Lightning was terrifying and mysterious. Some fish could shock you. Amber could pick up feathers. None of this seemed particularly useful. The first real breakthrough came in 1800 when an Italian physicist named Alessandro Volta built something he called a voltaic pile. It was essentially the first battery, a stack of alternating zinc and copper discs separated by cardboard soaked in salt water. And when you connected a wire to the top and bottom of this stack, current flowed, steady, continuous current. For the first time in history, humans had a reliable source of electric flow. It wasn't much, enough to make a wire warm, enough to produce a small spark, but it was real, and it was controllable. Volta had turned electricity from a phenomenon into a tool. Now, batteries are great for certain things, but they have a fundamental limitation that matters a lot for our story. They store a fixed amount of energy, and when it's gone, it's gone. You can't run a city on batteries, not in 1800, and honestly, not easily even today, though we're working on that. What you need, if you want to power anything at scale, is a way to continuously generate electricity. You need a machine that converts some other form of energy, motion, heat, falling water, into electrical current, and keeps doing it as long as you keep feeding it. And that's where Michael Faraday comes in. Faraday is one of those figures in science who deserves to be as famous as Einstein or Newton, and in engineering circles, he basically is. Born in 1791 in South London, he came from almost nothing. His father was a blacksmith who was frequently too ill to work, and the family was poor. Faraday had almost no formal education. At 14, he was apprenticed to a bookbinder, and the thing that saved him, the thing that changed the entire trajectory of human civilization, is that he read the books he was binding, particularly the science books. He became obsessed with chemistry and electricity, started attending public lectures by the famous chemist Humphrey Davy at the Royal Institution, took meticulous notes, bound those notes into a book, and sent them to Davy asking for a job. Davy eventually hired him as a laboratory assistant, and the rest is, well, it's literally the foundation of everything we're going to talk about tonight. In 1831, Faraday discovered electromagnetic induction, and this is worth slowing down for, because this single principle is the reason you have electricity in your home right now. Here's what he found. If you take a coil of wire and move a magnet through it, or move the coil past the magnet, it doesn't matter which one moves, an electric current appears in the wire. No battery needed, no chemical reaction, just motion and magnetism, and out comes electricity. The faster you move the magnet, the more current you get. The more coils of wire you use, the more current you get. It's beautifully simple and almost magical, and Faraday himself struggled to explain why it worked in mathematical terms. That mathematical framework would come later, from James Clerk Maxwell, but Faraday understood the principle intuitively and demonstrated it physically, and that was enough to change everything. Think about what this means. If you can spin a magnet inside a coil of wire, or spin a coil of wire around a magnet, you get electricity, continuously, as long as the spinning continues. And what can make things spin? Steam, falling water, wind, a hand crank, an engine. Suddenly, all the mechanical energy in the world, every waterfall, every steam engine, every turning wheel, could be converted into this invisible, transmittable force called electricity. Faraday had built a bridge between the mechanical world and the electrical world, and we have been walking across that bridge ever since. But here's the thing. Having the principle and having a practical system are very different things. Faraday's first generators were laboratory demonstrations. They produced tiny amounts of current. Making this work at any useful scale required decades of engineering refinement, and it required someone with not just scientific brilliance, but commercial ambition. Several someones, actually. But the one who matters most to the story of the power grid, the one who essentially willed it into existence through sheer force of personality, showmanship, and relentless experimentation, was Thomas Edison. Now, Edison is a complicated figure. He's been both overcredited and undercredited for various things, and the mythology around him can be frustrating if you care about historical accuracy. But one thing is genuinely true. Edison was the first person to conceive of electrical power not as a novelty or a laboratory phenomenon, but as a system. He didn't just want to make a light bulb, though he did spend an enormous amount of effort on that. He wanted to build the entire infrastructure needed to deliver electricity to paying customers. The generator, the wiring, the meters, the switches, the insulation, the light bulb itself, all of it designed to work together as one integrated commercial system. And in the late 1870s, that was a genuinely radical vision. Edison's approach was direct current, or DC. And we should talk about what that means, because the difference between direct current and alternating current is probably the single most important technical distinction in the entire history of the power grid, and it sparked, pun intended, one of the most vicious technological battles in American history. Direct current is simple to understand. The electrons flow in one direction, like water flowing through a pipe from a high point to a low point. You hook up a battery to a wire. Current flows from one terminal to the other, always the same direction, always steady. Edison's generators produced direct current. His light bulbs ran on direct current, and his whole system was designed around it. And it worked. On September 4th, 1882, Edison flipped the switch on the Pearl Street station in Lower Manhattan, and electric light flowed to 85 customers in a 1 square mile area. It was the first commercial central power station in the United States, and it was a genuine marvel. The New York Times building was one of the first customers, and the paper reported on the event with barely contained astonishment. But here's the problem with direct current, and it's a big one. DC doesn't travel well. When you push direct current through a wire, some of the electrical energy gets lost as heat. The wire itself has resistance, and the current has to fight through it. The longer the wire, the more energy you lose. And with the voltages Edison was using, about 110 volts, the losses were brutal. You couldn't economically send power much more than a mile from the generating station, which meant that if you wanted to electrify a whole city, you needed a power station on practically every block. Edison actually did this in parts of Manhattan. He built multiple stations, but it was enormously expensive, and it meant that electricity was basically a luxury for dense urban areas. Forget about suburbs. Forget about rural areas. Forget about sending power from a waterfall in the mountains to a city 50 miles away. With DC at low voltage, it just couldn't be done. And this is where the story takes a turn, because there was another way. Alternating current, AC, where the electrons don't flow steadily in one direction, but instead oscillate back and forth, switching direction dozens of times per second. Remember that vibrating dance I mentioned at the very beginning? That's alternating current. And alternating current has a property that changes everything, a property that makes the modern power grid possible. You can easily change its voltage. Let me explain why that matters, because it's one of those things that sounds dry but is actually the key to the whole puzzle. The amount of power you're transmitting through a wire is basically voltage multiplied by current. You can send a lot of power at high current and low voltage, or you can send the same amount of power at low current and high voltage. Same total power, different combination. Now here's the crucial part. The energy lost to heat in the wire depends on the current, not the voltage. Specifically, it depends on the current squared. So if you double the current, you quadruple the losses. But if you cut the current in half and double the voltage instead, same total power, you reduce the losses by a factor of 4. This means that if you want to send power over long distances without losing most of it to heat, you want to use very high voltage and very low current. And with alternating current, you can do that using a beautifully simple device called a transformer. A transformer is just 2 coils of wire wrapped around a shared iron core. You feed AC into one coil, and AC comes out the other coil, but at a different voltage. If the second coil has more turns of wire than the first, the voltage goes up and the current goes down. If it has fewer turns, the voltage goes down and the current goes up. No moving parts, no fuel, almost no energy lost. It's one of the most elegant devices in all of engineering, and it only works with alternating current. You cannot do this trick with DC, not with a simple passive device anyway. Edison's direct current was stuck at whatever voltage the generator produced, and that was that. So the potential advantages of AC were enormous. You could generate electricity at a moderate voltage, step it up to very high voltage for long-distance transmission. We're talking thousands or even tens of thousands of volts. Send it across miles of wire with minimal losses, and then step it back down to a safe, usable voltage at the other end. One power plant could serve an entire region. The economics were completely different. And the people who saw this most clearly were a brilliant, eccentric Serbian-American inventor named Nikola Tesla and a shrewd, ambitious industrialist named George Westinghouse. Tesla had been thinking about alternating current since his student days in Graz, Austria, in the late 1870s. The story goes that he was walking in a park in Budapest in 1882, the same year Edison opened Pearl Street, when the solution to a problem that had been nagging him suddenly crystallized in his mind. He saw, complete and whole, the design for an AC motor that used rotating magnetic fields. He reportedly sketched it in the dirt with a stick. Whether that specific detail is perfectly accurate, who knows? Tesla was a gifted self-mythologizer. But the engineering was real, and it was revolutionary. He had figured out how to make alternating current do useful mechanical work, not just light bulbs, but motors, which meant AC could power factories, streetcars, elevators, everything. Tesla came to America in 1884 and actually worked for Edison briefly. It did not go well. The two men were almost comically opposite in temperament and method. Edison was a tireless empiricist. He would test thousands of variations of something until he found what worked, brute forcing his way to solutions. Tesla was a theoretician and a visualizer who could design entire machines in his head, rotate them mentally, and predict how they would perform before building a single prototype. Edison reportedly dismissed AC as dangerous and impractical. Tesla thought Edison's commitment to DC was stubborn and short-sighted. Tesla left Edison's employ. There's a disputed story about a promised bonus that was never paid, and eventually found his way to George Westinghouse. Westinghouse was already interested in AC. He had bought the American patent rights to a transformer design from European inventors Lucien Gillard and John Dixon Gibbs, and he had hired a talented engineer named William Stanley, who had built a working AC distribution system in Great Barrington, Massachusetts, in 1886. When Tesla showed up with his AC motor patents, Westinghouse saw the final piece of the puzzle. He licensed Tesla's patents and began building a complete AC power system to rival Edison's DC empire. And Edison did not take this lying down. What followed was one of the strangest, most dramatic, and frankly most disturbing episodes in the history of technology. A propaganda war that came to be known as the War of Currents. Edison, who had built his reputation partly on the safety of his low-voltage DC system, launched a campaign to convince the public that alternating current was lethally dangerous. And the methods he used were genuinely shocking, even by the rough standards of the Gilded Age. Edison funded public demonstrations where animals were electrocuted using alternating current. Dogs, calves, even a horse, brought before audiences and killed with AC to prove how dangerous it was. He didn't always do this personally, but he funded and encouraged it, and his associates, particularly a man named Harold P. Brown, carried out these demonstrations with Edison's laboratory resources and his tacit blessing. Brown toured the country with these grim spectacles, and Edison's publicity machine made sure newspapers covered everyone. Now, here's what's important to understand. Edison wasn't entirely wrong that AC could be dangerous. Higher voltages are more dangerous to the human body, and AC systems operated at higher voltages than Edison's DC. But the argument was deeply misleading, because the whole point of AC was that you could step the voltage up for transmission, and then step it back down to safe levels before it entered anyone's home. The danger Edison was demonstrating was real, but irrelevant to how AC would actually be used in practice. It was like arguing that cars are too dangerous because you showed people what happens when you drive one off a cliff. Technically accurate, completely misleading. But the most disturbing chapter in this propaganda war involved something much darker than animal demonstrations. In the late 1880s, New York State was looking for a more humane method of execution to replace hanging. A dentist named Alfred Southwick had witnessed an accidental electrocution and thought electricity might offer a quick, painless death. A commission was formed, and Harold Brown, Edison's associate, lobbied aggressively for the new electric chair to use alternating current. The logic was cynical and transparent. If AC became associated with execution, with death, the public would never want it in their homes. Edison himself, when asked, recommended alternating current for the purpose. He even suggested that the act of being executed this way should be called being Westinghoused. The first person executed by electric chair was William Kemmler on August 6, 1890, at Auburn Prison in New York. And it was not the quick, painless death that had been promised. The first jolt didn't kill him. Witnesses reported that Kemmler was still breathing after the current was turned off, and a second, longer application was needed. The scene was, by all accounts, horrific. George Westinghouse reportedly said afterward, "They would have done better using an axe." It was a grim moment, and it's worth pausing here to acknowledge the human cost of what was, at its core, a business rivalry. A man died badly, in part because two industrial empires were fighting over which kind of electricity would power the future. But here's the thing. And this is where the story takes a turn that Edison probably didn't expect. The electric chair debacle didn't actually turn public opinion against AC the way he'd hoped. If anything, it made people uneasy about the whole spectacle of the propaganda war itself. And meanwhile, the technical advantages of AC were becoming impossible to ignore. The numbers were just too compelling. You could transmit AC power over dozens of miles with manageable losses. DC still couldn't go more than a mile or so without requiring another generating station. As cities grew, as demand for electricity expanded beyond a few blocks of downtown Manhattan, DC's limitations became a practical wall that no amount of publicity could overcome. The moment that really settled the debate, or at least began settling it, came in 1893 at the World's Columbian Exposition in Chicago. This was a massive World's Fair, celebrating the 400th anniversary of Columbus's arrival in the Americas, and it was going to be the most spectacular display of electric lighting the world had ever seen. Edison's General Electric Company bid on the contract to illuminate the fair. So did Westinghouse. And Westinghouse won, partly because his AC system was simply cheaper to install and operate at that scale. The fair needed to light an enormous area, over 600 acres, and running DC at that distance would have been absurdly expensive. When the fair opened its gates and President Grover Cleveland pressed a button to turn on the lights, over 100,000 incandescent bulbs blazed to life, all powered by alternating current. It was breathtaking. For millions of visitors, many of whom had never seen electric light at all, this was their first encounter with the future. And it was AC that was delivering it. The Columbian Exposition didn't just showcase electricity. It showcased AC electricity, specifically, at a scale that made the technology undeniable. And then came Niagara Falls. This is one of those projects that deserves some time because it represents the moment when the power grid, as a concept, truly began to take shape. People had been dreaming about harnessing Niagara Falls for industrial power for decades. The sheer volume of water going over those falls, more than 700,000 gallons per second, represented an almost incomprehensible amount of energy just thundering into the gorge, unused. In 1890, a group of financiers formed the Niagara Falls Power Company and established an international commission to figure out how to do it. The commission was chaired by Lord Kelvin, one of the most respected physicists alive, and initially, Kelvin favored DC. He was skeptical of AC. But as the commission reviewed proposals and evaluated the engineering, the advantages of AC became clear. They needed to transmit power not just to the factories at the base of the falls, but to the city of Buffalo, 26 miles away. DC couldn't do it. AC could. Westinghouse won the contract to build the generators and the transmission system. Tesla's polyphase AC system, using multiple alternating currents offset in timing from each other, was at the heart of the design. And this is worth pausing on for a moment because polyphase power is one of those ideas that sounds complicated, but is actually beautifully elegant once you see what it's doing. Think about it this way. A single alternating current rises and falls in a smooth wave. It peaks, drops to zero, goes negative, comes back to zero, peaks again, over and over. That means there are moments in each cycle where the current is passing through zero, delivering no power at all. For a light bulb, that's fine. The filament stays hot through those zero crossings, and you never notice the flicker. But for a motor, those zero power moments create problems. The motor's torque fluctuates, it vibrates, it's inefficient. Tesla's insight was to use multiple currents, staggered in time, so that when one current is passing through zero, another is at its peak. If you use 3 currents, each offset by 1/3 of a cycle, you get something remarkable. The total power delivered is constant and smooth, never dropping to zero. And when you feed those 3 currents into a motor with the right arrangement of coils, you create a rotating magnetic field that spins smoothly and continuously, like an invisible hand turning the motor's shaft. That's 3-phase power, and it's the same system that powers virtually every electrical grid on Earth today. The motors in factories, the compressors in your refrigerator, the pumps that push water through municipal systems, they're all running on the same basic principle Tesla worked out in the 1880s. The Niagara Falls Power Station went online on November 16, 1896, and began transmitting electricity to Buffalo. It worked. 26 miles of AC transmission, stepping the voltage up to 11,000 volts for the journey, then stepping it back down for distribution in the city. Factories in Buffalo that had been running on steam could now run on electricity generated by falling water, miles away. It was the proof of concept that changed everything. Within a few years, power companies across the country were building AC systems. The war of currents was effectively over, even if Edison never quite admitted defeat. General Electric, the company that had grown out of Edison's original enterprises, quietly began manufacturing AC equipment. Now here's something worth thinking about as you're lying there. The war of currents wasn't really about which technology was better in some abstract sense. It was about which technology could scale. Edison's DC system worked beautifully for a small, dense area, a few city blocks of wealthy customers in Lower Manhattan. It was safe, it was reliable, and Edison had built a genuine engineering marvel at Pearl Street. But it couldn't grow. It couldn't reach beyond its own neighborhood without building another complete generating station every mile or so. A C could scale because transformers let you trade voltage for current and vice versa. which meant you could move power efficiently over long distances. And that ability to scale, to send electricity from where it's generated to where it's needed, even if those places are far apart, is the fundamental thing that makes a power grid a grid rather than just a collection of isolated generating stations. And that's actually a really important distinction, because the early electrical systems weren't grids at all. They were islands. Each power station served its own little territory, running at whatever voltage and frequency the local company happened to choose. There was no standardization. Some systems ran at 25 cycles per second, some at 50, some at 60, some at 133. Voltages varied wildly. If you lived on one side of a street served by one company, and your neighbor across the street was served by a different company, your electrical systems were completely incompatible. You couldn't share power between them. You couldn't connect them. Each one was its own tiny, self-contained world. And this is where the story of the power grid shifts from being about individual inventors and their rivalries to being about something much messier and more interesting: the slow, chaotic, often reluctant process of connecting all these little islands together into something larger. Because it turns out that connecting power systems together is enormously beneficial, but it's also enormously complicated. And the reasons for both the benefits and the complications come down to some fascinating physics that most people never think about. The key idea, and this is one of those concepts that seems simple on the surface but gets deeper the more you look at it, is something called synchronization. And synchronization in a power grid isn't like syncing your phone to the cloud or matching up a playlist. It's something much more physical, much more immediate, and honestly, kind of beautiful once you understand what's actually happening. So let's talk about it. When we say an AC power system runs at 60 cycles per second, which is what most of North America settled on, and we'll get to why in a bit, what we mean is that the voltage is oscillating back and forth 60 times every second. The current flows one direction, reverses, flows the other direction, reverses again, and that complete back and forth cycle happens 60 times in the span of a single second. That's the frequency. 60 hertz. In Europe and most of the rest of the world, it's 50 hertz, 50 cycles per second. But the principle is the same. Now here's the thing. If you have two generators running independently, each one producing AC at 60 hertz, you might think, great, they're both at the same frequency. Just wire them together, and you've got twice the power. But it's not that simple. Because frequency isn't the only thing that matters. What also matters is phase, which is just a fancy way of saying, are the two generators hitting their peaks and valleys at exactly the same instant? Imagine two people on swings next to each other. They might both be swinging at the same speed, same frequency. But if one person is at the top of their forward swing, while the other person is at the bottom of their backward swing, they're completely out of phase. And if you tried to physically connect those two swings with a rigid bar, something would break. The forces would fight each other. That's essentially what happens if you try to connect two AC generators that are out of phase. The voltages don't add up. They clash. You get enormous currents surging between the two machines, not flowing out to customers but just circulating destructively between the generators themselves. Equipment overheats. Windings can burn out. Circuit breakers trip. In the worst case, you can physically damage the generators, which are massive, expensive machines that take months to build and install. So connecting two AC systems together requires that they be synchronized. Same frequency, same phase, same voltage, all matched up precisely before you close the switch that links them. And this is where it gets really interesting, because once you do successfully synchronize two generators and connect them, something almost magical happens. They lock together. They hold each other in step. If one generator tries to speed up slightly, the electrical connection to the other generator acts like a kind of invisible elastic bond, pulling it back into sync. If one tries to slow down, the same thing happens in reverse. The generators, once connected, behave almost like they're mechanically coupled, even though the only connection between them is the electrical wires. This phenomenon is sometimes called synchronous lock or synchronous coupling, and it's one of the most important and least appreciated features of AC power systems. Think about what that means. You can have a generator in one city and another generator 50 miles away, and once they're synchronized and connected through transmission lines, they effectively rotate in lockstep. Their rotors, the massive spinning parts inside each generator, sometimes weighing hundreds of tons, are turning at precisely the same electrical speed, their magnetic fields rising and falling in perfect unison, separated by miles of wire but bound together by the laws of electromagnetism. It's like a dance where the partners can't see each other, but are perfectly coordinated anyway. And this synchronous coupling is what makes a grid possible. Because once you understand that synchronized generators naturally hold each other in step, you can start connecting more and more of them together. 3 generators, 10, 100, thousands, and they all lock together into one enormous synchronized system, all oscillating at the same frequency, all rising and falling together 60 times a second across an entire continent. Right now, as you're lying there, every generator connected to your power grid, and there are thousands of them, is spinning in synchrony. The grid itself is like one giant machine, the largest machine ever built by human beings, and every part of it is locked into this shared electrical heartbeat. But here's the kicker. That heartbeat isn't perfectly steady. It wobbles, it fluctuates, and managing those fluctuations is one of the great ongoing engineering challenges of running a power grid. Here's why. At every single moment, the total amount of electricity being generated across the grid has to exactly match the total amount of electricity being consumed. Not roughly match, not mostly match. Exactly match, in real time, instant by instant. And when I say exactly, I mean it. There is essentially no storage in a traditional power grid. Electricity is generated and consumed in the same instant. It's not like water, where you can fill up a reservoir and draw from it later. The grid is a just-in-time system, and the balance between supply and demand has to be maintained continuously. So what happens when the balance shifts? Say it's a hot afternoon, and millions of people come home from work and turn on their air conditioners within the span of about 30 minutes. Demand surges. Suddenly, the grid needs more power than the generators are currently producing. Now, you might think the lights would just dim or something, and eventually they might. But the first thing that actually happens is much more interesting and much more physical. The extra load, all those air conditioners, acts as a drag on the generators. Remember, these generators are massive spinning machines, turbines connected to rotors, and the electrical load they're serving is directly felt as a mechanical resistance on those spinning rotors. More load means more resistance. More resistance means the rotors start to slow down, just slightly. And when the rotors slow down, the frequency drops. Instead of exactly 60 hertz, maybe it dips to 59.98 hertz, maybe 59.95. That doesn't sound like much, does it? A tiny fraction of a hertz, but the grid is exquisitely sensitive to frequency. Grid operators monitor frequency constantly, down to thousandths of a hertz, because frequency is the single most important real-time indicator of whether supply and demand are in balance. If frequency is exactly 60 Hz, the grid is perfectly balanced. If frequency drops below 60, it means demand is exceeding supply. The generators are being dragged down by the load. If frequency rises above 60, it means there's more generation than demand. The generators are speeding up because they're not working as hard. And this is genuinely elegant when you think about it. The frequency of the entire grid acts as a universal, instantaneous signal that tells every operator and every automated control system exactly what's happening with the supply-demand balance, everywhere, all at once. You don't need to measure demand at every single outlet and factory and streetlight. You just look at the frequency. If it's dropping, you need more generation. If it's rising, you need less. It's like the grid has a pulse, and you can take that pulse from anywhere on the system and get the same reading. So what do grid operators do when frequency starts to drop? They bring more generation online. They signal power plants to increase their output. Gas turbines can ramp up relatively quickly. Some peaker plants can go from standby to full power in 10 or 15 minutes. Hydroelectric plants can respond even faster, sometimes in seconds, because all you have to do is open the gates and let more water flow through the turbines. Coal and nuclear plants are much slower to respond, which is why they're typically used for baseload, the steady, predictable foundation of power that runs all the time. While faster responding plants handle the fluctuations on top. But here's where it gets really fascinating from an engineering standpoint. In the moments before those additional generators can ramp up, those critical seconds and minutes right after demand spikes, what keeps the grid from collapsing? What bridges the gap? And the answer is one of the most beautiful pieces of hidden engineering in the entire system. It's the kinetic energy stored in all those spinning generators. Remember, the rotors of large power plant generators are enormous. A typical turbine generator rotor in a big coal or nuclear plant might weigh 200 tons or more, and it's spinning at 3,600 revolutions per minute for a 60 Hz system. That's 60 revolutions per second. The amount of kinetic energy stored in that spinning mass is tremendous, and when demand suddenly exceeds supply, the grid doesn't instantly black out. Instead, it draws on that stored kinetic energy. The rotors slow down slightly. That's where the frequency drop comes from. And as they slow down, they release some of their rotational energy into the electrical system, automatically and instantaneously covering the gap between supply and demand. The generators act as a kind of flywheel, a buffer, buying time for the control systems to respond and bring more generation online. This property is called inertia, and it's one of those things that power engineers have relied on for over a century without most people ever knowing it exists. Every large spinning generator on the grid contributes to this shared pool of inertia, and collectively, it gives the grid a kind of resilience, a resistance to sudden changes. The more spinning mass you have on the system, the more inertia you have, and the slower the frequency changes when supply and demand get out of balance. It's like the difference between trying to slow down a bicycle wheel and trying to slow down a freight train. The freight train has so much inertia that it takes a lot more force to change its speed. And this, by the way, is one of the reasons why the modern transition to renewable energy is more complicated than a lot of people realize. Solar panels and wind turbines connected through electronic inverters don't have spinning mass in the same way that traditional generators do. A solar panel has no rotor. It has no inertia. When you replace a large coal plant with a solar farm, you get clean energy, which is wonderful. But you also lose the inertia that coal plant was contributing to the grid. And that means the grid becomes more sensitive to sudden changes in supply and demand. The The frequency swings faster, and the control systems have less time to respond. It's a solvable problem. Engineers are developing synthetic inertia and fast-responding battery systems and all kinds of clever solutions. But it's a real engineering challenge that comes directly from the physics of how grids maintain their balance. Now let me take you back to the early 1900s for a moment, because the people building the first interconnected power systems didn't have any of this figured out yet. They were learning it the hard way, through trial and error, and occasionally through spectacular failures. And one of the most important early steps in grid development happened not because of some grand vision of a unified electrical system, but for a much more practical reason: money. Specifically, the economics of sharing electricity across boundaries. See, in the early days, every power station was its own little kingdom. A utility company would build a generating station, wire up a neighborhood or a factory district, and that was it. Their system was an island. If their generator tripped offline, their customers went dark. If demand was low on a Sunday morning, their generator was still spinning, burning fuel, producing power that nobody needed. And if demand spiked on a hot afternoon, well, they just had to hope their equipment could handle it, because there was no one to call for help. And this is where the economics come in. Building a power plant is expensive. Running it inefficiently is expensive. And keeping a spare generator sitting idle just in case your main one breaks down, that's really expensive. But here's the thing. If you could connect your system to your neighbor's system, suddenly the math changes completely. Your peak demand and their peak demand probably don't happen at exactly the same time. Maybe your customers are mostly residential, so your peak is in the evening when everyone comes home and turns on the lights. But your neighbor's customers are mostly factories, so their peak is during the day shift. If you connect your two systems together, you can share generating capacity. During the day, their generators help serve your load. In the evening, your generators help serve theirs. Neither of you needs to build as much total capacity as you would if you were operating alone. You share the peaks, and you share the reserves, and everybody saves money. This idea, it's called diversity of load, and it's one of the most powerful economic principles in the entire history of electrical engineering. It sounds simple, almost obvious, but it fundamentally changed how power systems were built. Because once utilities realized they could save money by interconnecting, they started doing it. Not everywhere at once, and not without enormous technical headaches. But the economic incentive was strong enough to push through the difficulties. The first significant interconnections in the United States started appearing around 1905 to 1910. And they were modest affairs, a tie line between two neighboring utilities, maybe running at a few thousand volts, allowing them to share power back and forth. But even these small connections revealed something important. When two systems were tied together, both systems became more reliable. If one generator tripped, the other system could instantly pick up the slack, and the lights stayed on. The frequency dipped a little, the remaining generators worked a little harder, but the customers never noticed, and that reliability benefit turned out to be just as valuable as the economic savings, maybe more so. Now, I should mention that these early interconnections weren't always smooth. Remember what we talked about with synchronization, matching frequency, voltage, and phase before you can connect two AC systems? In the early 1900s, this was genuinely difficult. Different utilities operated at different frequencies. Some ran at 25 Hz, some at 50, some at 60, some at 40, and a few at oddball frequencies like 33 or 133 Hz. Different voltages, different phase configurations, some single phase, some two phase, some three phase. Trying to connect two systems that operated at different frequencies was essentially impossible without some kind of conversion equipment, and that equipment was expensive and lossy. So the first interconnections only worked between utilities that happened to use compatible standards. And this is actually how standardization happened in the United States. It wasn't decreed from above by some government agency. It emerged organically from the economic pressure to interconnect. If you wanted to tie your system to your neighbors and share the benefits of diversity, you needed to be on the same frequency. And gradually, through a combination of industry consensus and practical necessity, the country converged on 60 hertz. It took decades. Some 25 hertz systems in the northeastern United States persisted well into the mid-20th century, particularly for railroad electrification. But the trend was clear. Standardization wasn't about elegance. It was about money. Let me tell you about one of the most important early figures in grid interconnection, because his name doesn't come up nearly as often as Edison or Tesla, but his contribution to the modern power grid is arguably just as significant. Samuel Insull. He was British-born, came to America in 1881 as Edison's personal secretary, just 21 years old, and he was brilliant at business in a way that Edison, for all his genius, frankly wasn't. Insull understood something that most early electrical pioneers missed. He understood that electricity was not like other products. You couldn't store it. You couldn't manufacture it in advance and put it in a warehouse. You had to produce it at the exact moment it was consumed. And that meant the economics of electricity were fundamentally different from the economics of, say, steel or textiles. Insull moved to Chicago in 1892 to run Chicago Edison, and over the next 3 decades, he transformed the electricity business. He was the one who really figured out load factor, the ratio of average demand to peak demand. A utility that only served residential customers had a terrible load factor because everyone wanted power at the same time in the evening, and the generator sat nearly idle the rest of the day. But if you could mix residential load with commercial load and industrial load, you could keep your generators running efficiently around the clock. Different customers peaked at different times, and the generator didn't care who was using the power. It just needed to stay loaded. So Insull aggressively pursued every kind of customer. He didn't just wire up wealthy neighborhoods. He went after factories, streetcar systems, office buildings, department stores. He offered cheap rates to customers who would use power during off-peak hours. He basically invented the concept of demand-based pricing for electricity. And it worked spectacularly. By spreading the load across different types of customers, he could run his generators at higher capacity factors, which meant his cost per kilowatt hour dropped, which meant he could offer lower prices, which attracted more customers, which improved his load factor even further. It was a virtuous cycle, and Insull rode it all the way to building one of the largest utility empires in American history. But here's what really matters for our story. Insull understood that bigger was better when it came to power systems. Larger generators were more efficient than smaller ones. Larger systems with more diverse loads were more economical than smaller ones. And interconnected systems were more reliable than isolated ones. So he pushed relentlessly for consolidation and interconnection. He bought up smaller utilities across Illinois and the Midwest. He built transmission lines to connect them. He created holding companies that controlled vast networks of power systems spanning multiple states. By the 1920s, Insull's empire served something like 4 million customers across 32 states. And the technical infrastructure he built, the high-voltage transmission lines, the interconnected generating stations, the centralized dispatch. This was the prototype for the modern grid. He wasn't just selling electricity. He was building a machine, a continent-spanning machine, where generators hundreds of miles apart were synchronized together, spinning in lockstep at 60 hertz, sharing load and backing each other up. Now, Insol's story doesn't have a happy ending, and it's worth pausing on because it tells you something important about the relationship between engineering and finance. His holding company structure, companies owning companies, each layer leveraged with debt, worked beautifully as long as electricity demand kept growing and stock prices kept rising. But when the Great Depression hit in 1929, the whole edifice came apart. Electricity demand fell. Revenue fell. The debt payments didn't. By 1932, Insol's empire had collapsed. He lost everything. He was indicted for fraud, though eventually acquitted, and he died in 1938 in a Paris metro station with just 84 cents in his pocket. It's a genuinely tragic story. The man who arguably did more than anyone to create the modern power grid died essentially penniless and disgraced. But the grid he built survived. That's the important part. The physical infrastructure, the transmission lines, the interconnected generators, the operating principles, all of that outlasted the financial structure that had been built on top of it. And in the aftermath of Insol's collapse, the federal government stepped in with the Public Utility Holding Company Act of 1935, which broke up the giant utility empires and established federal regulation of interstate electricity sales. The grid became a regulated utility, a public service, something too important to be left entirely to the whims of financial speculators. And this brings us to one of the most fascinating aspects of the power grid: the tension between its physical reality as an engineering system and its economic reality as a marketplace. Because the grid is both. It's a machine governed by the laws of physics, where electrons flow according to Kirchhoff's laws, and generators must stay synchronized or the whole thing falls apart. But it's also a marketplace, where electricity is bought and sold, where prices fluctuate based on supply and demand, where companies compete and cooperate, and sometimes game the system. And these two realities don't always sit comfortably together. Physics doesn't care about contracts. Electrons don't read invoices. When you inject power into the grid at one location and withdraw it at another, the electricity doesn't flow along the contractual path. It flows along every available path according to the impedance of the transmission lines. This is called loop flow, and it's one of the most counterintuitive things about how power grids actually work. You might have a contract to sell power from a generator in Ohio to a customer in Virginia, but some of that power will physically flow through Pennsylvania, and some might even loop up through New York, depending on the network topology and the impedances of the lines. The electrons take every parallel path, dividing up according to the resistance and reactance of each route, and there's nothing you can do about it short of physically disconnecting lines. This creates all kinds of interesting problems. A utility in Pennsylvania might find that its transmission lines are congested not because of its own customers, but because of power flowing through its territory from a transaction between two other utilities that it has nothing to do with. This is called inadvertent flow, or parallel path flow, and managing it is one of the ongoing challenges of operating an interconnected grid. It's the kind of problem that wouldn't exist if every utility were an island, but the benefits of interconnection are so enormous that everyone accepts the complications. and those complications only grew as the grid expanded through the middle of the 20th century. After World War II, electricity demand in the United States exploded. Air conditioning became widespread. Suburbs sprawled, factories hummed, and the grid grew to meet that demand, with larger and larger generating stations, higher and higher voltage transmission lines, and more interconnections between utility systems. By the 1960s, the eastern United States was essentially one giant synchronized machine. Thousands of generators, tens of thousands of miles of transmission lines, all operating in lockstep at 60 hertz. And then, on November 9th, 1965, that machine showed everyone just how interconnected it really was. It was a Tuesday evening, about 5:17 p.m., and a backup relay on a transmission line near Niagara Falls. Actually, let me back up a little, because this story deserves to be told properly. And to understand what happened, you need to understand something about how transmission lines are protected and what happens when a protection relay trips. So picture a transmission line, one of those big, high-voltage lines strung between lattice steel towers marching across the countryside. That line is carrying an enormous amount of power, maybe hundreds of megawatts, and the current flowing through it generates heat. The line has a thermal rating, a maximum amount of current it can carry before the conductor sags too much or gets damaged. But heat isn't the only danger. Lightning can strike. A tree can fall into the line. Ice can build up and snap a conductor. Two lines can swing together in the wind and arc. Any of these events can create a short circuit, which is called a fault, and when a fault happens, the current through the line can spike to many times its normal level in a fraction of a second. If you don't clear that fault quickly, and quickly means within a few cycles, a few 60ths of a second, the enormous current will destroy equipment, melt conductors, and potentially damage generators that are feeding power into the fault. So every transmission line has protective relays. These are devices that monitor the current and voltage on the line, and when they detect conditions that indicate a fault, they send a signal to circuit breakers to open and disconnect the faulted line from the rest of the system. This happens automatically, faster than any human could react. The relay sees the fault, makes a decision, and trips the breaker, all within maybe 5 cycles, less than 1/10 of a second. And here's the important thing. Relays have settings. Someone has to decide what conditions should trigger a trip. Too sensitive, and the relay trips the line unnecessarily, taking a perfectly good line out of service when nothing is actually wrong. Too insensitive, and the relay fails to clear a real fault, which can be catastrophic. Getting those settings right is one of the critical but invisible jobs in power system engineering. Now, back to November 9th, 1965. The system that failed was a set of 5 transmission lines running north from the Sir Adam Beck Generating Station No. 2 at Niagara Falls, Ontario. This is on the Canadian side, carrying power up to Toronto. These lines had protective relays, and one of those relays, on a line called Q29, had a setting that had been configured back in 1963. At the time the setting was chosen, the power flow on that line was lower. But over the following 2 years, load had grown. More power was flowing north to Toronto, and nobody had gone back and updated the relay setting to reflect the new, higher normal operating conditions. So by the evening of November 9th, 1965, the power flowing through that line during the peak evening demand was actually very close to the relay's trip threshold. Not because anything was wrong, but simply because load had grown and the relay setting hadn't kept up. At 5:16 p.m., the power flow on line Q29 nudged just above that threshold. The relay did exactly what it was designed to do. It saw a current level that exceeded its setting, and it tripped the breaker. The line disconnected. But here's the thing. The power that had been flowing on Q29 didn't disappear. It still needed to get to Toronto. So it instantly redistributed onto the 4 remaining lines. And now those 4 lines were each carrying more power than before. Their relays saw the increased flow, and one by one, in rapid succession, they tripped too. Within seconds, all 5 lines connecting Niagara Generation to Toronto were open. Now you've got a massive amount of generation at Niagara that's suddenly lost its load. The generators speed up because they're still producing power, but have nowhere to send it. Meanwhile, Toronto has lost a huge chunk of its supply, but Toronto is connected to the rest of Ontario, and Ontario is connected to New York, and New York is connected to New England, and all of this is one big synchronized machine. So the power that was supposed to go north to Toronto now surges south and east into New York State, looking for a path. The tie lines between Ontario and New York, which were designed to carry a certain amount of power, are suddenly slammed with a massive unexpected flow. Those lines overload, and their protective relays trip them too. And now you've got a cascade. Each line that trips pushes more power onto the remaining lines, which overloads them, which causes their relays to trip, which pushes even more power onto fewer and fewer lines. It's like dominoes, but electrical dominoes falling at nearly the speed of light. Within minutes, the cascade had spread across the entire northeastern United States and parts of Ontario. Generators tripped offline to protect themselves. Load was lost. The frequency, which remember has to stay right at 60 Hz, went haywire. Some areas saw it spike as generators lost their load. Other areas saw it plummet as they lost supply. The system broke apart into islands, and most of those islands couldn't sustain themselves. They blacked out. 30 million people lost power. New York City went dark. Boston, Rochester, Buffalo, Toronto, all dark. It was the largest blackout in history at that time. And the remarkable thing is that nobody had done anything wrong in the moment. No operator made a bad decision. No equipment malfunctioned. The relay on Q29 did exactly what its settings told it to do. The problem was that the setting was outdated, and the system had no mechanism to catch that kind of slow drift between operating conditions and protection settings. It was a systemic failure, an emergent property of a complex interconnected system where a small misconfiguration in one corner could cascade across an entire continent. Now, here's what's worth pausing on. The blackout lasted about 13 hours in most areas, and considering that 30 million people were suddenly plunged into darkness, on a November evening, the social response was remarkably calm. There was very little looting, very little panic. People helped each other. Strangers directed traffic at intersections where the signals had gone dark. There's a famous, probably apocryphal, story about a spike in the birth rate 9 months later, but the actual demographic data doesn't really support it. What the blackout did produce, though, was a fundamental rethinking of how the grid was managed. Before 1965, reliability coordination was mostly voluntary and informal. Utilities cooperated because it made economic sense, but there was no mandatory framework for ensuring that the interconnected system as a whole was operated safely. After the blackout, the industry formed the North American Electric Reliability Council, NERC, in 1968. Initially, NERC was a voluntary organization. It developed reliability standards and guidelines, and utilities were expected to follow them, but there was no legal enforcement mechanism, It took another 40 years and another catastrophic blackout before those standards became mandatory. But we'll get to that. The 1965 blackout taught the industry several specific lessons. One was that protection relay settings need to be coordinated across the entire interconnected system, not just within individual utility boundaries. Another was that operators need better real-time visibility into what's happening on the grid, not just their own piece of it, but the neighboring systems too. And a third, maybe the most fundamental, was that in a tightly interconnected system, you need to plan for contingencies. You need to operate the system so that it can survive the loss of any single element, any one transmission line, any one generator, without cascading. This principle became known as N-1 security. The system should be operated so that if you take away any one component, that's the -1. The remaining system, the N-1, can handle the redistribution of power without any further trips or violations. Think about what that means in practice. It means you can never run the grid right at its limits. You always have to hold something in reserve. Every transmission line has to have enough spare capacity that if the line next to it trips, it can absorb the extra flow. Every region has to have enough generation that if its largest plant trips, the remaining plants can pick up the slack. It's a conservative philosophy, and it costs money. You're essentially paying for capacity you hope you'll never need. But the alternative is cascading blackouts, and that costs far more. And this is a good moment to talk about something that makes the grid genuinely different from almost any other engineered system, which is the timescale on which things happen. When that relay tripped on line Q29, the cascade propagated across the northeastern grid in about 5 minutes. 5 minutes to go from a single relay operation in Ontario to 30 million people without power. The electrical phenomena, the redistribution of power flows, the frequency deviations, the voltage swings, these happen in seconds or fractions of seconds. The mechanical responses of the generators, the governors adjusting steam valves, the rotors swinging against each other, these happen over seconds to tens of seconds. The human operators, sitting in control rooms looking at their displays, trying to understand what's happening and decide what to do, they operate on a time scale of minutes. And in a fast cascade, minutes is too slow. This is why so much of grid protection is automated. The relays, the automatic generation control systems, the under-frequency load-shedding schemes, these all operate without human intervention because they have to. A human can't react fast enough. But automation has its own risks because automated systems do exactly what they're programmed to do. And if the programming doesn't account for an unusual situation, like a relay setting that hasn't been updated in 2 years, the automation can make things worse instead of better. There's a deep tension in power system engineering between the need for fast automated response and the need for human judgment, and finding the right boundary between those two is something the industry is still working on. So after 1965, the grid continued to grow and evolve, but now with a much greater awareness of reliability as a system-wide concern. The 1970s brought new challenges. The oil crisis forced utilities to diversify their fuel sources, and suddenly the mix of generation on the grid started to change. Nuclear power expanded rapidly. Coal plants got bigger, and a new idea started to take hold, one that would eventually transform the entire structure of the electricity industry. The idea was simple, almost obvious in retrospect, but it was radical at the time. What if generating electricity and delivering electricity didn't have to be done by the same company? For decades, the model had been vertical integration. One utility owned the generators, owned the transmission lines, owned the distribution wires, and served the customers. That was Insol's model, and it worked well enough. But by the late 1970s and into the 1980s, people started asking whether competition in generation might drive down costs. The argument was that transmission and distribution were natural monopolies. It doesn't make sense to build two sets of wires down the same street. But generation wasn't. Anyone could build a power plant. And if you opened up the generation market to competition, market forces would push toward efficiency and innovation. This idea gained traction with the Public Utility Regulatory Policies Act of 1978, PURPA, which required utilities to buy power from certain qualifying independent generators, particularly those using renewable energy or cogeneration. It was a crack in the wall of vertical integration, and that crack would widen dramatically in the 1990s when the Federal Energy Regulatory Commission issued Orders 888 and 889, which essentially required utilities to open their transmission systems to all generators on equal terms. The idea was called open access, and it meant that if you owned a transmission line, you couldn't give your own generators preferential treatment over someone else's. You had to let competitors use your wires at the same price you charged yourself. Now, think about what that means in the context of everything we've talked about. The physics of power flow, the way electricity takes every available path according to impedance, the problem of parallel path flow, the need for real-time balancing of supply and demand. You're taking a system that was designed and operated as an integrated whole, where the same engineers who dispatched the generators also manage the transmission lines, and you're splitting it apart. The people deciding which generators to run are now different from the people managing the wires. And the electricity doesn't care about the contracts or the market rules. It still flows according to physics. So you need a new kind of entity, someone who sits in the middle and manages the transmission system independently, making sure the physics work regardless of who's buying and selling the power. These entities became known as Independent System Operators, or ISOs, and later Regional Transmission Organizations, or RTOs, and they are among the most important institutions in the modern power grid that most people have never heard of. They're the air traffic controllers of electricity. They don't own the planes, they don't own the airports, but they're the ones in the tower, making sure everything moves safely and nothing crashes into anything else. The way it works is actually pretty elegant once you see it. An ISO or RTO operates a control room, a big one usually, with banks of screens showing the real-time state of the entire transmission network across a wide region. They can see power flows on every major line, voltage levels at every substation, the output of every generator, and the total demand across the system, all updating every few seconds. And their job is threefold. First, reliability. Keeping the lights on, making sure the physics work, ensuring no line gets overloaded, no voltage sags too low, no frequency drifts. Second, they run the wholesale electricity market, deciding which generators get dispatched each hour, each 15 minutes, sometimes each 5 minutes, based on competitive bids. And third, they plan for contingencies, constantly running simulations to ask, if this line trips right now, or if that generator suddenly goes offline, will the rest of the system hold? That N-1 criterion we talked about earlier, the lesson from the 1965 blackout, that's not just a nice idea anymore. It's an operational requirement that these control rooms enforce in real time. The first ISO in the United States was PJM, which stands for Pennsylvania, New Jersey, Maryland, though it's since expanded to cover a much larger area stretching from the mid-Atlantic coast all the way into parts of the Midwest. PJM actually has roots going back to 1927, when utilities in that region formed a power pool to share resources, so it had decades of experience coordinating across company boundaries before it was formally restructured as an ISO in 1997. The California ISO, CAISO, also launched in the late 1990s. So did the New York ISO and the New England ISO, and eventually MISO, the Mid-Continent Independent System Operator, and SPP, the Southwest Power Pool, and ERCOT in Texas, which is its own fascinating story. Let's talk about ERCOT for a second, because it illustrates something really fundamental about how interconnection and regulation intersect. ERCOT stands for the Electric Reliability Council of Texas, and it manages the grid for most of Texas. And here's what makes it unique. The Texas grid is, by design, almost entirely electrically isolated from the rest of the country. There are only a couple of small DC ties connecting it to the eastern and western interconnections. And the reason for this goes back to that question of federal jurisdiction. Under the U.S. Constitution, the federal government regulates interstate commerce. If your power lines cross state boundaries, FERC has authority over you. But if your grid stays entirely within one state, if electrons on your system never cross a state line, then you're outside federal jurisdiction. Texas utilities figured this out decades ago and deliberately avoided building AC connections to neighboring states, keeping their grid self-contained so they could remain under state regulation rather than federal oversight. It's a remarkable example of how political boundaries and engineering decisions shape each other. The physics don't care about state lines, but the people building the system very much do. Now, this isolation has consequences. When the rest of the eastern interconnection has a problem, Texas is insulated from it. They won't get dragged into someone else's cascading failure. But it also means Texas can't easily import power from its neighbors during an emergency. And that vulnerability was exposed in devastating fashion in February 2021, when Winter Storm Uri hit Texas with temperatures far below what the system was designed for. Natural gas wells froze. Gas pipelines lost pressure. Power plants that depended on gas couldn't get fuel. Wind turbines iced up. Even some coal piles froze solid. In the span of a few days, roughly a third of ERCOT's generating capacity went offline. We're talking about tens of thousands of megawatts just gone. Demand, meanwhile, was spiking as everyone turned up their electric heaters. The gap between supply and demand grew so large, so fast, that the grid frequency started dropping dangerously. ERCOT later said the system came within about 4 minutes of a total, uncontrolled collapse, a complete blackout that could have taken weeks to recover from. Because when you lose the entire grid at once, you have to restart every generator from scratch, and many generators need external power to start up. It's a bootstrapping problem, like trying to start a car when the battery is dead and there's no one around to give you a jump. To prevent that total collapse, ERCOT ordered massive controlled load shedding, deliberately cutting power to millions of customers. And those outages lasted not minutes, not hours, but days. In freezing temperatures, with no heat, no water pressure because water treatment plants lost power, pipes bursting everywhere. The human cost was staggering. Estimates vary, but hundreds of people died, many from hypothermia in their own homes. It was one of the worst infrastructure disasters in modern American history. And here's the thing. The engineering lessons from Uri Echo lessons that were already known. Weatherization of power plants, making sure they can operate in extreme cold, is standard practice in northern states and in Canada. The techniques exist. Insulating pipes, heat tracing instrument lines, winterizing cooling systems. None of this is exotic technology. But Texas had never required it because extreme cold was considered unlikely. The economic incentive wasn't there in a market that rewarded low-cost generation. Spending money to protect against a once-in-a-generation freeze looked like wasted investment until it wasn't. It's the same pattern you see over and over in engineering disasters. The failure isn't usually in the physics. It's in the assumptions about what conditions the system will face. So let me bring this back to the broader picture of how these restructured grids actually operate day to day, because the market mechanics are genuinely fascinating once you understand them. In an RTO-managed market, generators submit bids, essentially saying, I can produce this many megawatts at this price per megawatt hour. The RTO's computers then stack up all the bids from cheapest to most expensive, and they dispatch generators in order, starting with the cheapest until they've got enough supply to meet demand. This is called a merit order dispatch, or sometimes a security-constrained economic dispatch, because the RTO also has to check that the resulting pattern of generation won't overload any transmission lines. If the cheapest combination of generators would push too much power through a particular corridor, the RTO might have to skip a cheap generator and use a more expensive one somewhere else to keep flows within limits. And that's where something called locational marginal pricing comes in. The price of electricity at each node in the network can be different, reflecting both the cost of generation and the cost of congestion on the transmission system. Think about what that means. Electricity at a substation in downtown Chicago might have a different price than electricity at a substation in rural Iowa at the exact same moment, even though they're on the same interconnected grid. The price difference reflects the physical reality that getting power from Iowa to Chicago requires transmission capacity, and if that capacity is scarce, the price in Chicago goes up. It's the market's way of encoding the physics of power flow into economic signals. And those price signals, in theory, tell investors where to build new generators and new transmission lines, build generation near the expensive locations, build transmission to relieve the congested corridors. In practice, of course, it's messier than that. Building transmission lines takes years, sometimes decades, because you need rights of way across hundreds of miles of land, you need environmental reviews, you need to negotiate with every landowner and every county and every state along the route. And there's a fundamental allocation problem. If a new transmission line benefits customers in one state but runs through another state, who pays for it? This cost allocation question has stalled or killed more transmission projects than any engineering challenge ever has. The electrons are ready to flow. The technology exists. It's the institutional and political architecture that struggles to keep up. And this brings us to what might be the single biggest transformation the grid has ever faced. Something that dwarfs even the AC versus DC battle of the 1890s in its implications. Because everything we've discussed so far, the generators, the markets, the control rooms, the protective relays, the frequency regulation, all of it was built around a fundamental assumption that electricity is generated by large spinning machines located at known controllable points on the network and consumed by millions of distributed loads. The system was designed for one-way flow. Power moves from big central plants outward through the transmission system, down through the distribution system, and into your home. The control paradigm assumes that supply follows demand. When you flip on a light switch, somewhere a generator speeds up just a tiny bit to match. But now imagine that assumption starting to dissolve. Imagine millions of solar panels on rooftops, generating power that flows backward through the distribution system, from homes back up toward the substation. Imagine wind farms whose output depends on weather, not on market signals or operator commands. Imagine batteries in garages and basements that can absorb power or inject it depending on price signals. Imagine electric vehicles plugged in by the millions, each one a flexible load that could charge at midnight when power is cheap, or even feed power back to the grid during a peak evening hour. The entire topology of the system is inverting. Power flow is becoming bidirectional. Generation is becoming distributed and variable. And the old tools, the ones designed for a world of big, predictable spinning machines feeding passive consumers, those tools need to evolve. The challenge starts with something we spent time on earlier: inertia. Remember how those massive spinning rotors in conventional generators act like flywheels, storing kinetic energy that cushions the grid against sudden imbalances? Solar panels and wind turbines connected through power electronics don't naturally provide that. A solar inverter converts DC from the panels to AC at whatever frequency the grid is running, but it doesn't have a multi-ton rotor spinning at 3,600 revolutions per minute, storing energy in its rotation. So as renewables replace conventional generators, the grid loses inertia, and frequency becomes more fragile, more responsive to disturbances, harder to manage. And that's a real problem, because the grid has always relied on that cushion of spinning mass to buy time, even just a few seconds, for automatic controls to kick in and restore balance. So, what do? You can't exactly bolt a flywheel onto a solar panel. But here's what's clever. You can teach the inverter to pretend it has one. And that idea, that deceptively simple idea, is one of the most important engineering developments happening in power systems right now. It's called grid-forming inverter technology, and it represents a fundamental shift in how we think about power electronics on the grid. Let me explain the difference, because it matters. Traditional solar and wind inverters are what engineers call grid following. They look at the grid, they measure the voltage and frequency that's already there, set by those big spinning generators somewhere on the system. And they synchronize to it. They inject current in phase with the existing voltage waveform. They're followers. They need someone else to set the beat, and they dance along. This works fine as long as there are enough conventional generators out there providing that reference signal, that strong voltage waveform to lock onto. But as you retire more and more coal plants, more and more gas plants, as spinning machines become a smaller fraction of the generation mix, that reference signal gets weaker. The beat gets harder to follow. And in the extreme case, imagine an island grid or a microgrid running entirely on solar and batteries. There's no spinning machine at all. Who sets the frequency then? Who provides the voltage reference? Grid-following inverters just stare at each other, waiting for someone else to lead. Grid-forming inverters solve this. Instead of following the grid's voltage and frequency, they create it. They generate their own voltage waveform internally, and they push it out onto the network. They act like a voltage source, not a current source. And here's where it gets really elegant. Engineers program these inverters to mimic the physics of a synchronous generator. They build mathematical models of a spinning rotor into the inverter's control software. So when there's a sudden increase in load, the inverter's virtual rotor slows down, just like a real rotor would. And that slowdown causes the inverter to temporarily reduce its output frequency, which is exactly the signal the rest of the grid needs to recognize that there's an imbalance. The inverter doesn't have a physical flywheel, but it behaves as if it does. It synthesizes inertia from software and fast-acting battery storage or capacitors. Think about what that means. You're taking the physics that used to be an inherent property of the machine, the heavy spinning metal, the angular momentum, the stored kinetic energy, and you're recreating it digitally. The grid doesn't care whether the inertia comes from a 100-ton rotor or from a control algorithm running on a microprocessor, as long as the electrical behavior is the same. And in some ways, the synthetic version can actually be better, because you can tune it. You can make the virtual inertia constant larger or smaller. You can add virtual damping. You can program responses that no physical machine could achieve because of its fixed mechanical properties. This isn't theoretical anymore. It's being deployed. In 2020, the Australian energy market operator started requiring grid-forming capability for new battery installations in South Australia, partly because that region had already experienced what happens when you have too many grid-following inverters and not enough synchronous machines. On September 28, 2016, South Australia had a statewide blackout. The whole state went dark, after a severe storm knocked out transmission lines and a cascade of events led to a loss of synchronism. It was complicated, involving wind farm protection settings that tripped generation offline faster than expected, and the interconnector to the rest of Australia couldn't handle the sudden imbalance. The investigation revealed that the system had become more fragile than operators fully appreciated, in part because of the changing generation mix. That event, painful as it was, accelerated Australia's thinking about grid-forming inverters and synthetic inertia. The Hornsdale Power Reserve, that's the big Tesla battery that Elon Musk famously bet he could build in 100 days, was initially installed as a grid-following system, but it's been upgraded and expanded, and newer battery projects in the region are being built with grid-forming capabilities from the start. The UK's National Grid ESO has been running Stability Pathfinder contracts, essentially paying for providers of inertia and other stability services, because they recognize that as they shut down coal plants and even some gas plants, they need to procure those services from somewhere. Scotland, with its enormous wind resources, sometimes generates more renewable electricity than it consumes, and the stability challenges of operating a grid with very high inverter-based generation are being worked out there in real time. And here's the thing. This isn't just about inertia. Grid-forming inverters also help with fault current, which is another service that spinning machines naturally provide. When there's a short circuit on the grid, a tree falls on a power line, say, conventional generators dump a huge surge of current into the fault. That sounds bad, but it's actually essential because protective relays, remember those from our discussion of the 1965 blackout, they need to detect that surge of fault current to know something is wrong and to trip the right breakers to isolate the problem. Grid-following inverters are terrible at providing fault current. They're designed to limit their output to protect their delicate power electronics. So during a fault, they actually pull back, sometimes to almost nothing, right when the protection system needs a strong signal to work with. Grid-forming inverters can be designed to provide much more robust fault current, not as much as a giant synchronous generator, but enough to make the protection systems function correctly. So you've got this suite of services: inertia, frequency response, voltage support, fault current, that used to come for free, bundled with the energy from spinning generators, and now they need to be explicitly engineered into inverter-based resources. It's a bit like how a horse-drawn carriage came with its own heating system. The horse generated body heat, and when you replaced it with an automobile, you had to separately engineer a heater. The primary function changed, and the auxiliary services that came along for the ride had to be consciously recreated. Now, let's zoom out from the inverter level and think about what all of this means for how the grid is operated day to day, because the control room of a modern ISO is becoming a very different place than it was even 20 years ago. The traditional approach to operating the grid was built around a relatively small number of large dispatchable generators. An operator at PJM or MISO might be managing a few hundred generating units, each one big enough to matter individually, each one responding to dispatch signals, each one with known characteristics, ramp rates, minimum run times, heat rates. The system was complex, absolutely, but it was manageable because the number of controllable entities was in the hundreds, maybe low thousands. Now imagine a grid where a significant fraction of generation comes from millions of rooftop solar installations, tens of thousands of utility-scale solar and wind farms, hundreds of thousands of battery systems ranging from utility scale down to the power wall in someone's garage, and millions of electric vehicles that might participate in vehicle-to-grid programs. You can't dispatch those the way you dispatch a coal plant. You can't call up every homeowner with solar panels and ask them to curtail. The control architecture has to change fundamentally. This is where the concept of aggregation comes in. The idea is that a third party, sometimes called a virtual power plant operator or a distributed energy resource aggregator, bundles together thousands of small resources and presents them to the grid operator as a single manageable entity. From PJM's perspective, it looks like one resource offering, say, 50 megawatts of flexible capacity. But behind the scenes, that 50 megawatts might be assembled from 8,000 home batteries, 12,000 smart thermostats adjusting air conditioning loads, and a fleet of electric vehicles at a corporate campus. The aggregator handles the complexity of coordinating all those individual devices, and the ISO just sees a single bid in the market. FERC Order 2222, issued in September 2020, was a landmark in this space. It required all ISOs and RTOs to open their wholesale markets to distributed energy resource aggregations, removing barriers that had previously kept small resources from participating. Before that order, if you had a home battery, there was essentially no way for you to sell grid services into the wholesale market. The markets were designed for big generators. Order 2222 said, in effect, the grid of the future needs these resources, and the market rules need to accommodate them. Implementation has been slow and contentious. There are genuine technical challenges around telemetry, metering, and making sure the distribution system can handle the flows. But the direction is clear. And this brings up something fascinating about the distribution system itself, which for most of the grid's history has been the quiet, unglamorous part of the network. Transmission gets all the attention, the big high-voltage lines, the dramatic interconnections, the billion-dollar projects. Distribution is just the local stuff, the lines on wooden poles running down your street, the transformer on the pad outside your house. For a century, distribution engineering was relatively straightforward. Power flowed one way, from the substation out to customers. Voltage dropped gradually along the feeder, and you designed the system to make sure the voltage at the last house on the line was still within acceptable limits. Simple enough. But with rooftop solar, power flows backward. On a sunny afternoon in a neighborhood where every third house has solar panels, the feeder might actually be exporting power back through the substation. Voltage doesn't just drop along the line anymore, It can rise at points where solar injection is heavy, potentially exceeding the upper limits that equipment is rated for. The traditional voltage regulation devices, tap-changing transformers, capacitor banks, were designed for one-way flow and predictable load patterns. They can get confused by reverse flows and start hunting, switching back and forth as conditions fluctuate with passing clouds. This is why utilities are investing in what's sometimes called the smart grid, though that term has become so broad it's almost meaningless. More specifically, they're deploying advanced distribution management systems, software platforms that monitor and control the distribution network in something closer to real time. They're installing sensors on feeders that historically had almost no monitoring at all. They're upgrading to smart inverters on solar installations that can actively manage their reactive power output to help with voltage regulation, rather than just blindly pushing watts onto the wire. And this is where the grid starts to feel less like the industrial age infrastructure we've been tracing through history and more like an information technology system. The amount of data flowing through a modern grid is staggering. Phasor measurement units on the transmission system are streaming synchronized voltage and current measurements 60 times per second. Smart meters on homes are reporting consumption data every 15 minutes or every 5 minutes. Weather forecasts are being fed into machine learning models that predict solar and wind output hours or days ahead. Price signals are propagating through markets every 5 minutes in real-time dispatch. And all of this data has to be processed, interpreted, and acted upon, often automatically, because the timescales are too fast for human operators, which introduces a whole new category of vulnerability that the engineers who built the original grid never had to think about. When Samuel Insull was wiring Chicago in the 1910s, the threat model was pretty simple: storms, equipment failure, maybe a fire at the plant. Today, the grid is a cyber-physical system, meaning its physical operation is deeply intertwined with digital communications and software control, and that makes it a target. In December 2015, hackers, widely attributed to Russian state-sponsored groups, attacked the Ukrainian power grid, remotely opening breakers at 3 distribution companies and cutting power to roughly 230,000 customers. It was the first publicly confirmed cyber attack to cause a power outage. They did it again a year later, in December 2016, hitting a transmission substation near Kyiv with more sophisticated malware called Indestroyer, specifically designed to speak the communication protocols used by power grid equipment. The attackers didn't need to physically touch anything. They sent commands through the grid's own control systems. That sent a chill through every grid operator in the world, because the same types of control systems, the same communication protocols, are used everywhere. The North American grid has been hardening its cybersecurity posture through NERC's Critical Infrastructure Protection Standards, which mandate specific security controls for bulk electric system cyber assets. But the attack surface keeps expanding. Every smart inverter, every connected thermostat, every networked battery is potentially a point of entry. The more intelligent and connected we make the grid, the more we have to think about who's inside the system and what they can do once they're there. Because the old model of grid security was essentially a castle with a moat. You had a control center. It was physically secured. The communication links were dedicated leased lines, and the number of people who could interact with the system was small and known. But now the grid has millions of endpoints. Every rooftop solar inverter that can receive a firmware update over the internet is a potential doorway. Every smart meter that communicates back to the utility is a node in a vast network. And the challenge isn't just protecting the big obvious targets like power plants and transmission substations. It's protecting this enormous, sprawling edge of the grid that didn't even exist 20 years ago. Think about what a coordinated attack on distributed devices could look like. Researchers have actually modeled this. A team at Princeton published work in 2018 showing that if an attacker could simultaneously manipulate a large number of high-wattage, internet-connected devices, things like smart air conditioners, water heaters, electric vehicle chargers, they could create sudden, artificial swings in demand large enough to destabilize the grid. They called it a mad IoT attack, for manipulation of demand via Internet of Things. You wouldn't need to hack the utility at all. You'd hack the appliances, and the grid would see it as a sudden, unexplained surge or drop in load, exactly the kind of thing that trips protective relays and starts cascading failures. It's a completely different threat model from anything Samuel Insull, or even the engineers who designed SCADA systems in the 1970s, ever imagined. And here's what makes this so tricky to solve. The grid has to be open enough to function. You need communication between devices. You need remote monitoring and control. That's what makes the modern grid work. That's what enables all the beautiful real-time optimization we talked about, the 5-minute dispatch, the aggregation of distributed resources, the grid-forming inverters responding in milliseconds. You can't just disconnect everything and go back to manual switchgear and phone calls. So the challenge is building security into a system that, by its nature, has to be interconnected and responsive. It's like trying to build an immune system for something that has to keep breathing. NERC's, Critical Infrastructure Protection Standards, the CIP standards, have gone through multiple versions, each one more stringent. They cover everything from electronic security perimeters around control centers to personnel background checks to incident response plans. And they've genuinely improved the security posture of the bulk electric system, the big transmission-level infrastructure. But here's the thing. Those standards primarily apply to the bulk power system. Distribution-level assets, the stuff closest to your house, often falls under different regulatory frameworks, sometimes state-level, sometimes not regulated for cybersecurity at all. And that's exactly where the grid is getting more complex and more connected the fastest. So the industry is in this ongoing race, and it's a race that doesn't have a finish line. Every new capability you add to the grid, every smart inverter, every battery management system, every demand response platform, adds functionality and adds risk simultaneously. The engineers working on this aren't just electrical engineers anymore. They're working alongside cybersecurity specialists, software engineers, network architects. The skill set required to run a modern grid has expanded enormously compared to even the early 2000s. But let's step back from the threats for a moment, because I don't want to leave you with the impression that the grid is fragile or doomed. It's actually the opposite. The grid is remarkably resilient, and the reason it's resilient is because of everything we've been talking about all along. The layers of protection, the redundancy, the N-1 planning, the interconnections, the operators who train constantly for contingencies. The 2003 Northeast blackout, which we touched on earlier, was devastating. 50 million people lost power across the northeastern United States and Ontario, but it also led to the Energy Policy Act of 2005, which gave NERC's reliability standards the force of law. Before that, compliance was voluntary. After 2003, it became mandatory, with real financial penalties for violations. The system learned. It adapted. That's what the grid does. And that pattern, failure, investigation, improvement, runs through the entire history we've been tracing. The 1965 blackout gave us NERC. The 2003 blackout gave NERC enforcement teeth. Winter storm. Uri in 2021 led to new weatherization requirements in Texas and a hard conversation about market design and resource adequacy. The South Australia blackout of 2016 led to the Hornsdale Battery and a complete rethinking of how inverter-based resources should behave during faults. Every failure teaches something. Every failure makes the next version of the grid a little bit better. And the version of the grid that's emerging right now, the one being built and rebuilt as we speak, is genuinely extraordinary. Let me try to paint a picture of what it looks like when all these pieces come together, because we've talked about them individually, but the whole is something more than the sum of its parts. Imagine it's a Tuesday afternoon in April, maybe 2028 or 2030. The sun is shining across the southwest, and solar farms in Arizona, Nevada, and California are producing enormous amounts of electricity. At the same time, wind is blowing strong across the Great Plains, Kansas, Oklahoma, the Texas Panhandle. The grid operators in their respective control rooms, CAISO in Folsom, California, SPP in Little Rock, Arkansas, ERCOT in Austin, are watching their screens. But the screens look very different from what operators saw even a decade ago. They're seeing real-time data from phaser measurement units, refreshing 30 times per second, giving them a dynamic picture of grid conditions across thousands of miles. Machine learning models are forecasting what solar output will look like in 15 minutes, in an hour, in 3 hours, based on satellite imagery and weather data. The models are good, not perfect, but good enough to plan around. On the demand side, aggregators are managing hundreds of thousands of distributed resources. A virtual power plant in Southern California is coordinating 20,000 home batteries, adjusting their charge and discharge in response to price signals from the wholesale market. Smart thermostats in commercial buildings are pre-cooling spaces during the cheap, solar-rich afternoon hours so they can coast through the expensive evening peak without drawing as much power. Electric vehicles plugged in at workplaces are offering their batteries to the grid for frequency regulation, earning their owners a few dollars while they sit in the parking lot. All of this is happening automatically, orchestrated by software, governed by market rules that FERC and state regulators have spent years designing. And the inverters connecting all these resources to the grid aren't just passively pushing power anymore. The grid-forming inverters at the big solar and wind farms are actively maintaining voltage and frequency, providing the synthetic inertia that keeps everything synchronized. They're doing what spinning generators used to do, but they're doing it with algorithms and power electronics instead of steam and iron. The grid doesn't care where the stability comes from, as long as it's there. And it is. Now, here's what's really beautiful about this. From your perspective, lying in your bed, maybe in a house in some suburb, none of this is visible. Your lights work. Your phone is charging. The air conditioning hums along. The grid is doing this incredibly complex ballet of physics and economics and computation every second of every day, and you never have to think about it. That's the engineering achievement. Not just that it works, but that it's invisible. The best infrastructure disappears into the background of your life. And yet someone had to figure out every single piece of it. Someone had to figure out that alternating current could be transformed to different voltages, and that insight alone, Lucien Gaulard and John Dixon Gibbs with their early transformers, William Stanley perfecting the design for Westinghouse in 1886. That single idea is what made long-distance power transmission possible. Someone had to figure out that you could synchronize generators across hundreds of miles by keeping them all locked to the same frequency, 60 cycles per second in North America, 50 in most of the rest of the world. Someone had to figure out that when demand exceeds supply, frequency drops, and you can use that signal to coordinate the entire system. Someone had to figure out protective relaying, that you could build devices smart enough to detect a fault and isolate it in milliseconds before the damage spreads. Someone had to figure out that connecting regional grids together made everyone more reliable and more efficient, even though the politics and the economics of who pays for the transmission lines are still being argued about today. And someone had to figure out how to do all of this again, from scratch in some ways, for a grid that runs on wind and sunlight instead of coal and gas. That's the work that's happening right now, and it's some of the most challenging and consequential engineering of our time. The people working on grid-forming inverter control algorithms, on battery chemistry, on high-voltage direct current transmission lines that can move solar power from the deserts to the cities, on market designs that properly value flexibility and reliability. These people are solving problems that are every bit as hard as what Edison and Tesla and Westinghouse faced in the 1880s and 1890s. The tools are different. The physics is the same. You know, there's something deeply comforting about that continuity. The grid you're connected to right now, as you're lying there, is a direct descendant of the one Edison lit up on Pearl Street in September of 1882. Not metaphorically, literally. The wires run in an unbroken chain from those first generators to the outlet in your wall. The system has been rebuilt and expanded and transformed countless times, but it's never been turned off. The grid is one of the only machines humanity has ever built that has been running continuously for over a century. It's alive in a way that almost nothing else we've made is alive. It breathes with the rhythm of human activity, swelling in the morning when people wake up, peaking in the evening when they come home, quieting in the deep hours of the night, right about now, when most of the world around you is asleep, and the generators are still spinning. Somewhere, turbines are turning. Somewhere, inverters are switching on and off thousands of times per second, synthesizing clean sine waves from the DC output of solar panels that are, right now, facing the sun on the other side of the world. Somewhere, an operator is watching a screen, making sure the frequency is holding steady, making sure the voltage is where it should be, making sure that the power flows are balanced and the system is secure. They're doing it, so you don't have to think about it, so you can just lie here in the quiet and let the hum of the grid, that 60 hertz hum that's so constant you've stopped hearing it, carry you towards sleep. The grid will be there in the morning. It'll be there when you turn on the coffee maker, when you flip on the lights, when you check your phone. It'll be doing its work, invisible and reliable, the way it has for more than 100 years. And now, you know, at least a little bit, what's happening behind the outlet. The generators and the transformers and the transmission lines and the relays and the markets and the operators and the inverters and the batteries, all of it working together every second to keep the lights on. It's one of the greatest things we've ever built, and it's still getting better, but that's a story for another night. For now, just rest. The grid's got this.